Chapter 3 Magicians, the Master and the Heretic. Unlike the Ten Commandments, science was not handed to humankind on imposing tablets of stone. The story of science is the story of the rise and fall of numerous speculations, hypotheses, and models. Many seemingly clever ideas turned out to be false starts or led down blind alleys. Some theories that were taken to be ironclad at the time later dissolved when put to the various test of subsequent mere experiments and observations, only to become entirely obsolete. Even the extraordinary brainpower of the originators of some conceptions did not make those conceptions immune to being superseded. The great Aristotle, for instance, thought that stones, apples, and other heavy objects fall down because they seek their natural place, which is at the center of earth. As they approach the ground, Aristotle argued these bodies increased their speed because they were happy to return home. Air and fire, on the other hand, move upward because the air's natural place was with the heavenly spheres. All objects could be assigned a nature based on their perceived relation to the most basic constituents, earth, fire, air, and water. In Aristotle's words, in Aristotle's words, some existing things are natural, while others are due to other causes. Those that are natural are the simple bodies such as earth, fire, air, and water. All these things evidently differ from those that are not naturally constituted, since each of them has within itself a principle of motion and stability in space. A natural type of principle and cause of motion and stability within these things to which it primarily belongs. The things that are in accordance with nature include both these and whatever belongs to them in their own right, as traveling upward belongs to fire. Aristotle even made an attempt to formulate a quantitative law of motion. He asserted that heavy objects fall he asserted that heavier objects fall faster, with the speed being directly proportional to the weight. That is, an object 2 times heavier than another was supposed to fall at twice the speed. Whatever their experience might have made this law seem reasonable enough, a brick was indeed observed to hit the ground earlier than a feather dropped from the same height. Aristotle never examined his quantitative statement more precisely. Somehow, it either never occurred to him, or he did not consider it necessary, to check whether two bricks tied together in the fall twice as fast as a single brick. Galileo Galilei, 1564 until 1642, who was much more mathematically and experimentally oriented, and who showed little respect for the happiness of falling bricks and apples, who was the first to point out that Aristotle got it completely wrong. Using a clever thought experiment, Galileo was able to demonstrate that Aristotle's law just did not make any sense because it was logically inconsistent. He argued as follows: suppose you tie together two objects, one heavier than the other. How much would the combined object fall compared to each of its two constituents? On one hand, according to Aristotle's law, You might conclude that it would fall at some intermediate speed because the lighter object will slow down the heavier one. On the other, given that the combined object is actually heavier than its components, it should fall even faster than the heavier of the two, leading to a clever contradiction. The only reason that the theater falls on Earth more gently than a bit is that of the weather experiences greater resistance. It dropped out. It dropped from the same height in a vacuum that would hit the ground simultaneously. This fact has been demonstrated in numerous experiments, none more dramatic than the one performed by Apollo 15 astronaut by Apollo 15 astronaut David Randolph Scott. Scott, the seventh person to walk on the moon, simultaneously dropped a hammer from one hand and a feather from the other. Since the moon lacks a substantial atmosphere, the hammer and the feather struck the lunar surface at the same time. Amazing fact about Aristotle's false law of motion is not that it was wrong, but that it was accepted for almost 2000 years. How could a flawed idea enjoy such a remarkable longevity? This was a case of a perfect storm, three different forces combining to create an unanswerable doctrine. First, there was the simple fact that in the absence of precise measurements, Aristotle's law seemed to agree with experience-based common sense. Sheets of papyrus did not hover about with lumps of lead did not. It took Galileo's genius to argue that common sense could be misleading. Second, there was the colossal weight of Aristotle's almost unmatched reputation and authority as a scholar. After all, this was the man who laid the foundations for such a Western intellectual culture. Whether it was the investigation of all natural phenomena or the bedrock of ethics, metaphysics, politics, of art, Aristotle literally wrote the book, and that was not all. Aristotle, in some sense, even taught us how to think by introducing the first formal studies of logic. Today, almost every child at school recognizes Aristotle's pioneering virtually complete system of logical inference, known as a syllogism. Every geek is a person, every person is mortal, therefore every geek is mortal. The third reason for the incredible durability of Aristotle's incorrect theory was the fact that the Christian Church adopted this theory as a part of its artificial orthodoxy. This acted as a deterrent against small attempts to question Aristotle's assertions. In spite of his impressive contributions to the systemization of deductive logic, Aristotle is not noted for his mathematics. Somewhat surprisingly, perhaps, the man who essentially established science as an organized enterprise did not care as much, certainly not as much as Plato, for mathematics and was rather weak in physics. Even though Aristotle recognized the importance of numerical and geometrical relationships in the sciences, he still regarded mathematics as an abstract discipline divorced from physical reality. Consequently, while there is no doubt that he was an intellectual powerhouse, Aristotle does not make my list of mathematical magicians. I am using the term magicians here for those individuals who could pull rabbits out of literally empty heads, those who discovered never before thought of connections between mathematics and nature, those who were able to observe complex natural phenomena and to distill from the crystal clear mathematical laws. In some cases, these superior thinkers even used their experiments and observations to advance their mathematics. The question of unreasonable effectiveness of mathematics in explaining nature would never have arisen were it not for these magicians. This enigma was born directly out of the miraculous insights of these researchers. No single book can do justice to all the superb scientists and mathematicians who have contributed to understanding of the universe. In this chapter and the following one, I intend to concrete on only four of those giants of past centuries about whose status as magicians. There can be no doubt some of the creme de la creme of the scientific world. The first magician on my list is best remembered for a rather unusual event, for dashing starkly through the streets of his hometown. Give me a place to stand, and I will move the earth. When the historians of mathematics Eric Templeberg had to decide whom to name as his top three mathematicians, he concluded, any list of three greatest mathematicians of all history would include the name of Archimedes. The other two usually associated with him are Newton, 1642 until 1727, and Gauss, 1777 until 1855. Some, considering the relative wealth or poverty of mathematics and physical science in the respective ages in which these giants lived, and estimating their achievements against the background of their times, would put Archimedes first. Archimedes 287 until 212 BC. Figure 10 shows a bust claim to represent Archimedes, but which may in fact be that of a Spartan king. He was indeed the Newton or ghost of his day, a man of such brilliance, imagination, and insight that both of his contemporaries and their generations that follow him take his name in awe and reverence, even though he is better known for his ingenious inventions in engineering. Archimedes was primarily a mathematician, and in his mathematics, he was centuries ahead of his time. Unfortunately, little is known about Archimedes' early life of his family. His first biography, written by one Heraclides, has not survived, and the few details that we do know about his life and violent death come primarily from the writings of the Roman historian Plutarch, circa AD 46 until 120, was in fact more interested in the military accomplishments of the Roman general Marcellus, who conquered Archimedes' hometown of Syracuse in 212 BC. Fortunately for the story of mathematics, Archimedes had given Marcellus a tremendous headache during the siege of Syracuse that the three major historians of the period, Plutarch, Polybius, and Livy, could not ignore him. Archimedes was born in Syracuse, then a Greek settlement in Sicily. According to his own testimony, he was the son of the astronomer Phidias, about whom little is known beyond the fact that he had estimated the ratio of the diameters of the Sun and the Moon. Archimedes may have also been related in some way to King Hieron II, himself the legitimate son of a nobleman by one of the latter's female slaves. Irrespective of whichever ties Archimedes might have had with the royal family, both the king and his son Gelon always held Archimedes in high regard. As a youth, Archimedes spent some time in Alexandria, where he studied mathematics before returning to a life of extensive research in Syracuse. Archimedes was truly a mathematician's mathematician. According to Plutarch, he regarded assaulted an ignorable every art directed to use and profit, and he only strove after those things which in their beauty and excellence remain beyond all contact with the common needs of life. Archimedes' preoccupation with abstract mathematics and the level to which he was consumed by it apparently went much farther even than the enthusiasm commonly exhibited by practitioners of his discipline. Again, according to Plutarch, continually bewitched by a siren, whom always accompanied him, he forgot to nourish himself and omitted to care for his body, and when, as would often happen, he was ruled by force to bed and annoyed himself, he was still drawing geometrical figures in the ashes, or with his fingers would draw lines on his anointed body, being possessed by a great ecstasy and in truth a thrall to muses. In spite of his contempt for applied mathematics and the little importance that Archimedes seems to attach to his engineering ideas, his resourceful inventions gained him even more popular fame than his mathematical genius. The best-known legend about Archimedes further enhances his image as the stereotypical absent-minded mathematician. This amusing story was first told by the Roman architect Vitruvius in the 1st century BC, and it goes like this. King Hieron wanted to consecrate a gold wreath to the immortal gods. When the wreath was delivered to the king, it was equal in weight to the gold furnace for his creation. The king was none the less suspicious that a certain amount of gold had been replaced by silver of the same weight. Not being able to substantiate his distrust, this king turned for advice to the master of mathematicians, Archimedes. One day, the legend continued, Archimedes stepped into a bath. While still engrossed in the problem of how to uncover potential fraud with the wet, as he immersed himself in the water, however, realized that his body displayed a certain volume of water which overflowed the tube's edge. This immediately triggered the solution in his head. Overwhelmed with joy, Archimedes jumped out of the tub and ran naked in the streets shouting, Eureka! Eureka! I have found it! I have found it! Another famous Archimedean exclamation, Give me a place to stand, and I will move the earth. It currently fitted it in 1% of another on more than 150,000 web pages for in a Google search. This bold proclamation, sounding almost like the vision statement of a large corporation, has been cited by Thomas Jefferson, Mark Twain, and John F. Kennedy, and it was even featured in a poem by Lord Byron. The first was apparently the culmination of Archimedes' investigations to the problem of moving a given weight with a given force. Plutarch tells us that when King Hieron asked for a practical demonstration of Archimedes' ability to manipulate a large weight with a small force, Archimedes managed, using a compound pulley, to launch a fully loaded ship into the sea. Plutarch adds in admiration that he drew the ship along smoothly and safely as if she were moving through the sea. Slightly modified versions of the same legend appear in the other sources. While it is difficult to believe that Archimedes could have actually moved an entire ship with mechanical devices available to him at the time, the legends leave little room for doubt that he gave some specific demonstration to an invention that enabled him to maneuver heavy weights. Archimedes made many other peacetime inventions such as the hydraulic screw for raising water in a planetarium that demonstrated the motions of the heavenly bodies. But he but he became most famous in antiquity for his role in the defense of Syracuse against the Romans. Wars have always been popular with historians. Consequently, the event of the Roman siege on Syracuse during the year 214 until 12 BC have been lavishly chronicled by many historians. The Roman general Marcus Claudius Marcellus circa 260 until 200 8 BC. Biden, of considerable military fame, anticipated a rapid victory. He apparently failed to consider stubborn King Hiron, aided by a mathematical and engineering genius. Plutarch gives a vivid description of the havoc that Archimedes' machines inflicted upon the Roman forces. Archimedes, at once sought against the land forces all sorts of missile weapons and immense masses of stone that came down with incredible noise and violence, against which no man could stand, for they knocked down those upon when they fell in heaps, breaking all the ranks and files. At the same time, huge poles thrust out from the walls of the ship sank, some by great breaks, which they let down from on high upon them. Others they lifted up into the air by an iron hand of big like a crane big end, when they had drawn them up by the rope and set them on and up and set them and set them on end upon the poop. They plunged them to the bottom of sea. The ship was quickly lifted up to the great height in the air, a dreadful thing to behold, and was rolled to and fro, and kept swinging until the marines were all thrown out, when all at the length it was dashed against the rocks or let fall. The fear of the Archimedean devices became so extreme that if the Roman soldiers did but see a piece of rope of wood projecting above the wall, they would carry their edicts again, declaring that Archimedes was setting some engine in motion against them, and would turn their backs and run away. Even Marcellus was deeply impressed, complaining to his own crew of military engineers, "Shall we not make an end of fighting against the geometrical Briareus, the 100-armed giant, son of Uranus and Gaia, who, sitting at ease by the sea, plays speech and toss with our ships to our confusion, and by the multitude of missiles that he hurls at us, thus the 100-handed giants of mythology, according to another popular legend that appeared first in the writings of the great Greek physician Galen, circa AD 129 until 200. Archimedes used an assembly of mirrors that focused the sun's rays to burn the Roman ships. The 6th century Byzantine architect Anthemius of Tralles and a number of 12th-century historians repeated this fantastic story, even though the actual feasibility of such a feat remains uncertain. Still, the collection of almost mythological tales does provide us with rich testimony as to the veneration that the wise one inspired in later generations. As I noted earlier, Archimedes himself, the highly esteemed geometrical Briareus, attached no particular significance to all of his military toys. He basically regarded them as diversions of geometry at play. Unfortunately, this aloof attitude may have eventually cost Archimedes his life. When the Romans finally captured Syracuse, Archimedes was so busy drawing his geometrical diagrams on a dust filled tray that he failed to notice the tumble of war. According to some accounts, when a Roman soldier ordered Archimedes to follow him to Marcellus, the old geometer retorted indignantly, "Fellow, stand away from my diagram." This reply infuriated the soldier to such a degree that, disobeying his commander's specific orders, he unsheathed his sword and slew the greatest mathematician of antiquity. Figure 11 shows what is believed to be a reproduction for the 18th century of a mosaic found in Herculaneum, depicting the final moments in the life of the master. Archimedes' death marked, in some sense, the end of an extraordinarily vibrant era in the history of mathematics. As the British mathematician and philosopher Alfred North Whitehead remarked. The death of Archimedes at the hand of a Roman soldier is symbolical of a world change of the first magnitude. The Romans were a great race, but they were cursed by sterility which waits upon particularly. They were not dreamers enough. They were not dreamers enough to arrive at a new point of view, which could give more fundamental control over the forces of nature. No Roman lost his life because he was absorbed in the contemplation of a mathematical diagram. Fortunately, while details of Archimedes' life are scarce, many but not all of his incredible writings have survived. Archimedes had a habit of sending notes on his mathematical discoveries to a few mathematician friends or to people he respected. The exclusive list of correspondence included, among others, the astronomer Conon of Samos, the mathematician Aristotle of Cyrene, and the king's son Gelon. After Conon's death, Archimedes sent a few notes to Conon's then Dositheus of Pelusium. Archimedes' opus covers an astounding range of mathematics and physics. Among his many Among his many achievements, he presented general methods for finding the areas of a variety of plane figures and the volume of spaces bounded by all kinds of curved surfaces. These include the areas of the cycle, segments of a parabola and of a spiral, and volumes of segments of cylinders, cones, and other figures generated by the revolution of parabolas, ellipses, and hyperbolas. He showed that the value of the number, the ratio of the circumference of a cycle to its diameter, has been changed than smaller than at a time when no method existed to describe any larger numbers. He invented a system that allowed him not only to write down but also to manipulate numbers of any magnitude. In physics, Archimedes discovered the laws governing floating bodies, thus establishing the science of hydrostatic. In addition, he calculated the centers of gravity of many solids and formulated the mechanical laws of levers. In astronomy, he performed observations to determine the length of the year and distances to the planets. The work of many of the Greek the work of the Greek mathematicians were characterized by originally an attention to detail. Still, Archimedes' methods of reasoning and solution truly set him apart from all the scientists of his day. Let me describe here only three representative examples that give the flavors of Archimedes' inventiveness. One appears at first blush to be nothing more than an amusing curiosity, but a closer examination reveals the depth of his inquisitive mind. The other two illustrations of the Archimedean methods demonstrate such ahead of his time thinking that they immediately elevate Archimedes to what I dub the magician status. Archimedes was apparently fascinated by big numbers, but very large numbers are clumsy to express when writing in ordinary notation. Trying to a personal check for eight for try writing a personal check for 8.4 trillion dollars. The U.S. national debt in July 2006 in the space allocated for the figure amount. So Archimedes developed a system that allowed him to represent numbers with 80,000 trillion digits. He then used this system in an original treatise entitled the Saint Reckoner to show that the total number of cent grains in the world was not infinite. Even the introduction to this treatise is so illuminating that I will reproduce a part of it here. The entire piece was addressed to Gelon, the son of King Heron II. There are some King Gelon who think that the number of the sun is infinite is in multitude. And I mean by the sun not only that which exists about Syracuse and the rest of Sicily, but also that which is found in every region, whether inhabited or uninhabited. Again, there are some who, without regarding it as infinite, yet think that no number has been named which is great enough to exceed its multitude. And it is clear that they who hold this view, they imagine a mass made up of sand in other respects as large as the mass of the earth, including in it all the seas and hollows of the earth filled up to equal to that of highest of the mountains. Would be me, would be many times further still from recognizing that any number could be expressed with a sheet the multitude of the sand so taken. But I will try to show you by means of geometrical proofs which you will able to follow that of numbers named by me and give in work which I sent to Chef Sigbus, a work that has fortunately been lost. Some exceed not only the number of the masses of a set equal in magnitude to the earth filled up in the way described, but also that of a mass equal in magnitude to the universe. Now you are aware that universe is the name given by most astronomers to the sphere whose center is the center of the earth and whose radius is equal to the straight line between the center of the sun and the center of the earth. This is the common account as you have been heard from astronomers. But Aristarchus of Samos broke up brought out a book consisting of some hypotheses in which the premises lead to the result that the universe is many times greater than now so-called. His hypotheses are that the fixed stars and the sun remain removed, that the earth revolves about the sun in the circumference of a cycle, the sun lying in the middle of the orbit. This introduction immediately highlights the important points. One, Archimedes was able to question even very popular beliefs such as that there is an infinity grain of sand, and two, he treated with respect the heliocentric theory of the astronomer Aristarchus. Later in the treatise he actually corrected one of the Aristarchus hypotheses. In Aristarchus' universe, the Earth and the planets revolve around a stationary sun that was located at the center. Remember that this model was proposed 1800 years before Copernicus. After these preliminary remains, Archimedes starts to address the problem of the grains of sand, progressing a series of logical steps. First, estimate how many grains placed side by side it would take to cover the diameter of poppy seed. Then, how many poppy seeds would fit it in the breadth of a finger, how many fingers in a stadium about 600 feet, and continuing up to the 10 billion stadia. Along the way, Archimedes invented a system of indices and a notion that, where combined, allow him to classify gargantuan numbers. Since Archimedes assumed that the sphere of the fixed stars is less than 10 million larger than the sphere containing the orbit of the sun, as seen from the earth, he found the number of grains in sand packed universe to be less than 10 to 63 for one followed by 63 zeros. He found the number of grains in a sand universe to be less than 1 followed by 60 zeros. He then continued the treatise with a respectful note to Gelon. I conceive that these things, King Gelon, will appear incredible to the great majority of people who have not studied mathematics, but that to those who are conversant therewith, and have given through the question of the distances and size of the earth and sun and the moon and the whole universe, the proof will carry on confusion. And it was for this reason that I thought the subject would not be inappropriate for your consideration. The beauty of the sun recorder lies in the ease with which Archimedes hopes from everyday objects sand, poppy seeds, sand, fingers to abstract numbers and mathematical notation that, that make from those to the sciences of the solar system and the universe as a whole. Clearly, Archimedes possesses such intellectual flexibility that he could comfortably use his mathematics to discover unknown properties of the universe and use the cosmic characteristics to advance arithmetical concepts. Archimedes' second claim to the title of magician comes from the method that he used to arrive at many of his outstanding geometrical theorems. Very little was known about this method and about Archimedes' thought process in general until the 20th century. His concise style gave away very few clues. Then in 1906, a dramatic discovery opened a window into the mind of this genius. The story of this discovery shades so much like one of the historical mystery novels by the Italian author and philosopher Umberto Eco that I feel compelled to take the brief detour to tell it. Archimedes' palimpsest. Sometime in the 10th century, an anonymous scribe in Constantinople, today's Istanbul, copied the important works of Archimedes, the methods stomachon and on floating bodies. This was probably part of a general interest in Greek mathematics that was largely sparked by the 9th century mathematician Leo the Geometer. In 1204, however, the soldiers of the Fourth Crusade were lured by promises of financial support to sack Constantinople. In the years that followed, the pursuit of mathematics faded, while the schism between the Catholic Church of the West and the Orthodox Church of the East became a fait accompli. Sometime before 1229, the manuscript containing Archimedes' works underwent a catastrophic act of recycling. It was unbound and was so the parchment leaves could be reused for a Christian prayer book. The scribe Ioannis Myronas finished copying the prayer book on April 12, 12, April 14, 1229. Fortunately, the wasting of the original text didn't obliterate the writing completely. Figure 12 shows a page from the manuscript with the horizontal lines representing the prior text and the front vertical lines, the mathematical contents. By the 16th century, the palimpsest, the recycled document, somehow made its way to the Holy Land, to the monastery in Saint Sabas, east of Bethlehem. In the early 19th century, this monastery's library contained no fewer than 1,000 manuscripts. Still, for reasons that are not entirely clear, that Archimedes' palimpsest was moved yet again to Constantinople. Then, in the 1840s, the famous German biblical scholar Constantine Tischendorf, 1815 until 74, the discoverer of one of the earliest Bible manuscripts, visited the Mathematicon of the Holy Sepulchre in Constantinople, another house of the Greek Patriarchate in Jerusalem, and saw the palimpsest there. Tischendorf must have found the partially visible underlying mathematical text quite intriguing, since he apparently tore off and stole one page from the manuscript. Tischendorf's estate sold Tischendorf's estate sold that page in 1879 to the Cambridge University Library. In 1899, Greek scholar A. Papadopoulos Keramios catalogued all the manuscripts that were housed in the Mathematicon, and the Archimedes manuscript appeared as SMS 355 on his list. Papadopoulos Keramios was able to read a few lines of the mathematical text, and perhaps realizing the potential importance, he printed those lines in his catalogue. This was a turning point in the saga of his manuscript. The mathematical text in the catalogue was brought to the attention of the Danish philologist Johann Ludwig Heiberg, 1854 until 1928. Recognizing the text as belonging to Archimedes, Heiberg traveled to Istanbul in 1906, examined and photographed the palimpsest, and a year later announced his sensational discovery: two never-before-seen treatises of Archimedes, and one previously known only for its Latin translation. Even though Heiberg was able to read and later publish parts of the manuscript in his book on Archimedes' works, serious gaps remain. Unfortunately, sometime about 1908, the manuscript disappeared from Istanbul under mysterious circumstances, only to reappear in the possession of a Parisian family who claimed to have had it since 1920s. Improperly stored, the palimpsest has suffered some irreversible mold damage, and three pages previously transcribed by Heiberg were missing altogether. In addition, later than 1929, someone painted four Byzantine-style illuminations over 4 pages. Eventually, the French family that held the manuscript sent it to Christie's for auction. Ownership of the manuscript was disputed in the federal court in New York in 1998. The Orthodox Patriarchate of Jerusalem claimed that the manuscript had been stolen in the 1920s from one of its monasteries, but the judge ruled in favor of Christie's. The palimpsest was subsequently auctioned at Christie's on October 29, 1998, and it fetched $2 million for an anonymous buyer. The owner deposited the Archimedes manuscript at the World Text Art Museum in Baltimore, where it is still undergoing intensive conservation work and thorough examination. Only imaging scientists have in the arsenal tools not available to the earlier researchers: ultraviolet light, multispectral imaging, and even focused X-ray, to which the palimpsest was exposed at the Stanford Linear Accelerator Center, have already helped to decipher parts of the manuscript that had not been previously revealed. At the time of this writing, the careful scholarly study of the Archimedes manuscript is ongoing. I was fortunate enough to meet the palimpsest forensic team, and Figure 13 shows me next to the experimental setup as it illuminates the one page of the palimpsest at different wavelengths. The drama surrounding the palimpsest is only fitting for a document that gives us an unprecedented glimpse of the great geometers method. The method. When you read any book of Greek geometry, you cannot help but be impressed with the economy of style and the precision with which the theorems were stated and proved more than 2 millennia ago. What those books don't normally do, however, is give you clear hints as to how those theorems were conceived in the first place. Archimedes' exceptional document, the method, partially fills in this intriguing gap. It reveals how Archimedes himself became convinced of the truth of certain theorems before he knew how to prove them. Here is part of what he wrote to the mathematician Eratosthenes of Cyrene, circa 276 until 194 BC, in the introduction. I will send you the proofs of the theorems in this book, since, as I said, I know that you are intelligent. an excellent teacher of philosophy and greatly interested in any mathematical investigations that may come your way, I thought it might be appropriate to write down and set forth for you in December a certain special method by means of which you will be enabled to recognize certain mathematical equations with the aid of mechanics emphasis added. I am convinced that this is no less useful for finding the proofs of these same theorems. For some things which first become clear to me the mechanical method were afterwards proved geometrically, because this their investigation by this said method does not furnish an actual demonstration. For it is easier to supply the proof when we have previously acquired by the method some knowledge of the questions than it is to find it without any previous knowledge. Archimedes touches here on one of the most important points in scientific and mathematical research. It is often more difficult to discover what the important questions or theorems are than it is to find solutions to known questions for proofs to known theorems. So how did Archimedes discover some new theorems? Using his masterful understanding of mechanics, equilibrium, and the principles of the lever, he worked in his mind solids of figures whose volumes or areas he was attempting to find against ones he already knew. After determining in this way the answer to the unknown area of volume, he found it much easier to prove geometrically the correctness of the answer. Consequently, the method starts with a number of statements of centers of gravity and only then proceeds to the geometrical propositions and the proofs. Archimedes' method is extraordinary in two respects. First, he has essentially introduced the concept of thought experiment into rigorous research. The 19th century physicist Hans Christian Ørsted first dubbed this tool an imaginary experiment conducted in lieu of a real one, Gedanken experiment, in German, an experiment conducted in the thought. In physics, where this concept has been extremely fruitful, though experiments are used either to provide insights prior to performing actual experiments, or in cases where the early experiments cannot be carried out. Second, and more important, Archimedes freed mathematics from the somewhat artificial chains that Euclid and Plato had put on it. To these two individuals, there was one way, and one way only, to do mathematics. You had to start from the axioms and proceed by an inexorable sequence of logical steps, using well-prescribed tools. The free-spirited Archimedes, on the other hand, simply utilized every type of ammunition he could think of to formulate new problems and to solve them. He did not hesitate to explore and exploit the connections between the abstract mathematical objects, the Platonic forms, and physical reality, actual solids or flat objects, to advance his mathematics. A final illustration that further solidifies Archimedes' status as a magician is his anticipation of integral and differential calculus, a branch of mathematics formally developed by Newton and independently by the German mathematician Leibniz only at the end of the 17th century. The basic idea behind the process of integration is quite simple. Once it is pointed out, suppose that you need to determine the area of the segment of an ellipse. You could divide the area into many rectangles of equal width and sum up the areas of those rectangles with 14. Clearly, the more rectangles you use, the closer sum will get the actual area of the segment. In other words, the area of the segment is really equal to the limit that the sum of rectangles approaches as the number of rectangles increases to infinity. Finding this limit is called integration. Archimedes used some version of the method I have just described in to find the volumes and surface areas of the sphere, the cone, and of ellipsoids and paraboloids. The solid you get when you revolve ellipses or parabolas about their axis. In the differential calculus, one of the main goals is to find the slope of a straight line that is tangent to a curve at a given point. There is the line that touches the curve only at that point. Archimedes solved this problem for the special case of a spiral, thereby peeping into the future work of Newton and Leibniz. Today, the area of differential and integral calculus and the daughter branches form the basis on which most mathematical models are built, be it in physics, engineering, economics, or population dynamics. Archimedes changed the world of mathematics and it perceived relation to the cosmos in a profound way. By displacing an astounding combination of theoretical and practical interests, he provided the first empirical, rather than mythical, evidence of an apparent mathematical design of nature. The perception of mathematics being the language of the universe, and therefore the concept of God as a mathematician was born in Archimedes' work. Still, there was something that Archimedes did not do. He never discussed the limitations of his mathematical models when applied to actual physical circumstances. His theoretical discussion of levels, for instance, assumed that they were infinitely rigid and that rods had no weight. Consequently, he opened the door, to some extent, to the shaping of the appearances. Interpretation of mathematical models. This was the notion of mathematical models merely present what is observed by humans rather than describing the actual true physical reality. The Greek mathematician Geminus, circa 10 BC until AD 60, was the first to discuss in some detail the difference between mathematical modeling and physical explanations in relation to the motion of celestial bodies. He distinguished between astronomers or mathematicians who according to him had only to suggest models that would reproduce the observed motions in the heavens, and physicists who had to find explanations for the real motions. This particular distinction was going to come to a dramatic head at the time of Galileo, and I will return it later in this chapter. Somewhat surprisingly, perhaps, Archimedes himself, Archimedes himself considered as one of his most cherished accomplishment of the discovery to the volume of a sphere inscribed in a cylinder figure 15. Is always 2/3 of the volume of the cylinder. He was so pleased with this result, he requested it be engraved on his tombstone. Some 137 years after Archimedes' death, the famous Roman orator Marcus Tullius Cicero, circa 106 until 43 BC, discovered the great mathematician grave. Here Cicero rather moving description of the event. When I was a quaestor in Sicily, I managed to track down his Archimedes' grave. The Syracusans, the Syracusans knew nothing about it, and indeed denied that any such thing existed. But there it was, completely surrounded and hidden by bushes and bamboos and thorns. I remembered having of some simple lines of verse which had been inscribed on his tomb. Where it was were the cylinder model in stone on top of the grave. And so I took a good look around all the numerous tombs that stand beside the Agrigentine gate. Finally, I noted a little column just visible above the scarp. It was surmounted by a sphere and a cylinder. I immediately said to the Syracusans, some of whose leading citizens were with me at the time, that I believed this was the very object I had been looking for. Men were set in with seekers to clear the site, and when the path to the monument had been opened, we walked right up to it, and the faces were still visible, though approximately the second half of each line had been worn away. Some of the most famous cities in Greek world, and former days a great center of learning as well, who have remained in total ignorance of the tomb of the most brilliant citizen it had ever produced, had a man from Arpinum not come and pointed it out. Cicero did not exaggerate in describing Archimedes' greatness. In fact, I have deliberately put the bar for the title of magician so high that progressing from the giant Archimedes, we have to leap forward no fewer than about 18 centuries before encountering a man of similar stature. Unlike Archimedes, who said he could move the earth, this magician insisted the earth was already moving. Archimedes' best student, Galileo Galilei Figure 16, was born in Pisa on February 15, 1564. His father Vincenzo was a musician, and his mother Giulia Amanati was a witty, if rather ill-disposed woman who could not tolerate the stupidity. In 1581, Galileo followed his father's advice and enrolled in the Faculty of Arts of the University of Pisa to study medicine. His interest in medicine, however, withered almost as soon as he got it in favor of mathematics. Consequently, during the summer vacation of 1583, Galileo persuaded the mathematician of the Tuscan court, Ostilio Ricci, 1540 until 1603, to meet his father and to convince the latter that Galileo was destined to become a mathematician. Discussion was indeed settled soon thereafter. The enthusiastic youth became absolutely bewitched by the works of Archimedes. Those who read his works, he wrote, really realize only too clearly how inferior are all other minds compared with Archimedes, and what small hope is left of ever discovering things similar to the ones he discovered. At the time, little did Galileo know that he himself possessed one of those few minds that were inferior to that of Greek master, inspired by the legendary story of King Archimedes and the King's Rat. Galileo published in 1586 a small book entitled The Little Balance, about a hydrostatic balance he had invented. He later made further reference to Archimedes in literary lecture at the Florence Academy, in which he discussed a rather unusual topic, the location and size of hell in Dante's epic poem Inferno. In 1589, Galileo was appointed to chair of mathematics at University of Pisa, partly because of the strong recommendation of Christopher Clavius, 1538 until 1612, a respected mathematician and astronomer from Rome, whom Galileo visited in 1587. The young mathematician's star was now definitely on the rise. Galileo spent the next 3 years setting forth his first thoughts on the theory of motion. These essays, which were clearly stimulated by Archimedes' work, contain a fascinating mixture of interesting ideas and false assertions. For instance, together with the pioneering realization that one can test theories about falling bodies using an inclined plane to slow down the motion, Galileo incorrectly states that when bodies are dropped from towers, wood moves more swiftly than lead at the beginning of its motion. Galileo's inclinations and general thought process during this phase of his life have been somewhat misrepresented by his first biographer, Vincenzo Viviani, 1522 until 1703. Viviani created the popular image of meticulous, hard-nosed experimentalists who gained insights exclusively from the tight observations of natural phenomena. In fact, until 1592, until he moved to Padua, Galileo's orientation and methodology were primarily mathematical. He relied mostly on thought experiments on an Archimedean description of the world in terms of geometrical figures that obey mathematical laws. His chief complaint against Aristotle at the time was that the latter was ignoring not only the profound and more abstruse discoveries of the geometry, but even of the most elementary principles of the science. Galileo also thought that Aristotle relied too heavily on sensory experiences because they offer at first sight some appearance of truth. Instead, Galileo proposed to employ reasoning at all times rather than examples, for we seek the causes of effects, and these are not revealed by experience. Galileo's father died in 1591, prompting the young man, who had now to support his family, to take an appointment in Padua, where his salary was tripled. The next 18 years proved to be the happiest in Galileo's life. He have also begin. He in Padua he also began his long-term relationship with Marina Gamba, who whom he never married but who bore him these children, Virginia, Livia, and Vigenzio. In August 4, 1597, Galileo wrote a personal letter to the great German astronomer Johannes Kepler, in which he admitted that he had been a Copernican for a long time, adding that he found in the Copernican heliocentric model a way to explain a number of natural events that could not be explained by the geocentric routine. He lamented the fact, however, that Copernicus appeared to be ridiculed in his off the stage. This letter marked the widening of the momentous rift between Galileo and the Aristotelian cosmology. Modern astrophysics was starting to take shape. The Celestial Messenger. On the evening of October 9, 1604, astronomers in Verona, Rome, and Padua were started to discover a new star that rapidly became brighter than all the stars in the sky. The meteorologist Jan Budowski, an imperial official in Prague, also saw it on October 10, and in acute agitation he immediately informed Kepler. Clouds prevented Kepler from observing the star until October 17, but once he started, he continued to record his observations for a period of about a year, and he eventually published a book about the new star in 1606. Today we know that the 1604 celestial spectacle did not mark the birth of a new star, but rather the explosive death of an old one. This event, now called Kepler's supernova, caused quite a sensation in Padua. Galileo managed to see the new star with his own eyes late in October 1604, and following December and January he gave the public lectures on the subject to large audiences. Appealing to knowledge over superstition, Galileo showed that the absence of any apparent shift parallax in the new star's position against the background of the fixed stars demonstrated that the new star had to be located beyond the lunar region. The significance of this observation was enormous. In the Aristotelian world, all changes in the heavens were restricted to this side of the moon, while the far more distant sphere of the fixed stars was assumed to be inviolable and immune to change. The shattering of the immutable sphere had started already in 1572, when the Danish astronomer Tycho Brahe (1546 until 1601) observed another stellar explosion now known as Tycho supernova. The 1604 event put yet another nail in the coffin of Aristotle's cosmology. but the true breakthrough in the understanding of the cosmos did not descend from either realm of the theoretical speculation from naked observations. It was rather the outcome of simple experimentation with convex bulging outward and concave curving inward glass lenses. How the right two of those some 13 inches apart and distant objects suddenly appear closer. By 1608, such glasses started to appear all over Europe, and one Dutch and two Flemish spectacle makers even applied for patents on them. Rumors on the miraculous instrument reached the Venetian theologian Paolo Sarpi, who informed Galileo around May of 1609. Anxious to confirm the information, Sarpi also wrote to a friend in Paris, Jacques, Jacques Bardover, Jacques Badofer, to inquire whether the rumors were true. According to his own testimony, Galileo was raised with a desire for beautiful things. He later described these events in his book The Sidereal Messenger, which appeared in March 1610. About 10 months ago, a report reached my ears that a certain Fleming had constructed a spyglass by means of which by visible objects, though very distant from the eye of the observer, were distinctly seen as if nearby. Of this truly remarkable effect, several experiences were related, to which some persons gave credence while others denied them. A few days later, the report was confirmed to me in a letter from a noble Frenchman at Paris, Jacques Badofer, which caused me to apply myself wholeheartedly to investigate means by which I might arrive at the invention of a similar instrument. I did soon afterwards, my basis being the doctrine of refraction. Galileo demonstrates here the same type of creatively practical thinking that characterized Archimedes once he knew that a telescope could be built. It did not. It didn't take him long to figure out how to build one himself. Moreover, between August 1609 and March 1610, Galileo used his inventiveness to improve his telescope from a device that brought objects 8 times closer to an instrument with a power of 20. This was a considerable technical feat in itself, but Galileo's greatness was about to be revealed not in his practical know-how, but in the spirit of but in the use to which he put his vision enhancing tube, which he called a perspiculum. Instead of spying on distant ships on Venice harbor or examining the rooftops of Padua, Galileo pointed his telescope to the heavens. What followed was something unprecedented in scientific history. As the historian of science North Wedlow puts it, in about 2 months, December and January 1609 and 1610 respectively, he made more discoveries that changed the world than anyone has ever made before or since. In fact, the year 2009 has been named the International Year of Astronomy to mark the 400th anniversary of Galileo's first inventions. What did Galileo actually do to become such a larger-than-life scientific hero? Here are only a few of his surprising achievements with the telescope. Turning his telescope to the moon and examining in particular the terminator, the line dividing the dark and illuminated parts, Galileo found that this celestial body has a rough surface with mountains, craters, and vast plains. He watched how bright points of light appeared in the side fell in darkness, and how these pinpoints widened and spread just like the light of a rising sun catching on mountain tops. He even used the geometry of the illumination to determine the height of one mountain, which turned out to be more than 4 miles. But this was not all. Galileo saw the dark part of the moon in its crescent phase is also faintly illuminated, and he concluded that this was due to reflected sunlight from the earth. Just as the earth is lit by the full moon, as Galileo asserted the lunar surface betters, it reflected light from earth. While some of these discoveries were not entirely new, the stake of Galileo's evidence raised the argument to a whole new level. Until Galileo's time, there was a clear distinction between the terrestrial and the celestial, the earthly and the heaven and the earthly and the heavenly. The difference was not the difference was not just scientific or philosophical. A rich tapestry of mythology, religion, romantic poetry, and aesthetic sensibility have been woven around the perceived similarity between heaven and earth. Now Galileo was saying something that was considered quite inconceivable. Contrary to the Aristotelian doctrine, Galileo put the earth and heavenly body, the moon, on very similar footing. Both had solid, rugged surfaces, and both reflected light from the sun. Moving yet farther from the moon, Galileo started to observe the planets. The name coined by the Greeks were those wanderers in the night sky, directing his telescope to Jupiter on January 7, 1610. He was astonished to discover three new stars in a straight line crossing the planet, two, two to its two to its east and one to the west. The new stars appears to change their positions relative to Jupiter on following nights. On January 13, he observed a fourth such star. Within about a week from the initial discovery, Galileo reached a startling conclusion. The new stars were actually satellites orbiting Jupiter, just as the moon was orbiting the Earth. One of the distinguishing characteristics of the individuals who had a significant impact on the history of science was the ability to grasp immediately which discoveries was really likely to make a difference. Another trait of many influential scientists was their skill in making their discoveries intelligible to others. Galileo was a master in both of these departments. Concerned that someone else might also discover the Jovian satellites, Galileo rushed to publish his results, and by spring of 1610, his treatise Sidereus Nuncius, the sidereal messenger, appeared in Venice. Still politically astute at that point in his life, Galileo dedicated the book to the Grand Duke of Tuscany, Cosimo II de' Medici, and he named the satellites the Mathematician stars. 2 years later, following what he referred to as an Atlantic labor, Galileo was able to determine the orbital periods, the time it, the time it took each of the four satellites to revolve around Jupiter, to within an accuracy of a few minutes. The sidereal messenger became an instant bestseller. Its original 500 copies quickly sold out, making Galileo famous across the continent. The importance of the discoveries of the Jovian satellites cannot be overemphasized. Not only were these the first bodies to be added to the solar system since the observations of the ancient Greeks, but the more existence of the satellites removed in a single stroke one of the most serious objections to Copernicanism. The Aristotelians argued that it was impossible for the Earth to orbit the Sun, since the Earth itself had the Moon orbiting it. How could a universe have two separate centers of rotation, the Sun and the Earth? Galileo's discovery unambiguously demonstrated that a planet could have satellites orbiting it, while the planet itself was following its own course around the Sun. Another important discovery that Galileo made in 1610 was that of the phases of the planet Venus. In the geocentric doctrine, Venus was assumed to move in a small cycle and epicycle superimposed on its orbit around the Earth. The center on the epicycle was supposed to always lie on the line joining the Earth and the Sun, as figure in 17a, not drawn to scale. In this case, when orbiting, in this case, when observed from Earth, one could expect Venus always to appear as a crescent or somewhat varying width. In the Copernican system, on the other hand, Venus, Venus' appearance should change from a small bright disk when the planet is on the other side of the Sun is seen from Earth to a large and almost dark disk when Venus is on the same side as Earth. Figure 17b. When when those two positions, Venus should pass through an entire sequence of phases similar to that of Moon. Galileo corresponded about this important difference between the predictions of two doctrines with his former student Benedetto Castelli, 1570 until 1643, and he conducted the crucial observations between October and December of 1610. The verdict was clear. The observations confirmed conclusively the Copernican prediction, proving that Venus indeed orbiting the Sun. On December 11, a playful Galileo set Kepler to obscure anagram haec immatura a me iam frustra leguntrioi. This was already tried by me, in vain too early. Kepler unsuccessfully deciphered the hidden message and eventually gave up. In his following letter of January 1 on January 1st on January 1, 1611, Galileo finally transposed the letters in the anagram to read Cintiae figuras aemulatum mater amorum. The mother of love Venus emulates the figures of Cynthia the moon. All the findings I have described so far concern either planets in the solar system, celestial bodies that orbit the Sun and reflect its light, or satellites revolving around these planets. Galileo also made two very significant discoveries related to stars, heavenly objects that generate their own light, such as the Sun. First, he performed observations of the Sun itself. In the Aristotelian worldview, the Sun was supposed to symbolize otherworldly perfection and immutability. Imagine Imagine the shock caused by the realization that the solar surface is far from perfect. It contains blemish and dark spots that appear and disappear as the Sun rotates about its axis. Figure 18 shows Galileo's hand-drawn images of sunspots, about which Galileo's colleague Federico J.C. 1585 until 1630 wrote that they delight both by the wonder of the spectacle and the accuracy of expression. Actually, Galileo was neither the first to see sunspots, not even the first to write about them. One pamphlet in particular, three letters on sunspots, written by the Jesuit priest and scientist Christopher Scheiner, 1573 until 1650, annoyed Galileo so much that he felt compelled to publish an articulate reply. Scheiner argued that it was impossible for the spots to be right on the Sun's surface. His claim was based partly on the spots being, in his opinion, too dark. He thought that they were darker than the dark parts of the moon, and partly on the fact that he did not always appear to return to the same positions. Scheiner consequently believed that these were small planets orbiting the Sun. In his history and demonstrations concerning sunspots, Galileo systematically destroyed Scheiner's arguments one by one, with a meticulousness, wit and sarcasm that would have made Oscar Wilde jump to a standing ovation. Galileo showed that the spots were in fact not dark at all, only dark relative to the brighter solar surface. In addition, Galileo's work left no doubt that the spots were right on the sun's surface. I shall return to Galileo's demonstration on this fact later in this chapter. Galileo's observations of other stars were truly the first human adventures into the cosmos that lies beyond our solar system. Unlike his experience with the moon and the planets, Galileo discovered that his telescope hardly enlarged the images of stars at all. The implication was clear: stars were far more distant than planets. This was a surprise in itself, but was truly eye-popping what the sheer number of new faint stars that the telescope had revealed. In one small area around the constellation Orion alone, Galileo discovered no fewer than 500 new stars. When Galileo turned his telescope to transverse the Milky Way, that patch of dim light that crosses the night sky, he was in for the biggest surprise yet. Even the smooth-looking bright splash brought into a countless number of stars no human had ever seen as such before. The universe suddenly got much bigger. In the somewhat dispassionate language of a scientist, Galileo reported, "What was observed by us in the third place is the nature of matter of the Milky Way itself, which, with the aid of the spyglass, may be observed so well that all the disputes that for so many generations have vexed philosophers are destroyed by visible certainty, and we are liberated from worldly arguments. For the galaxy is nothing else than a congeries of innumerable stars distributed in clusters. To whatever region of it you direct your spyglass, an immense number of stars immediately offer themselves to view, of which very many, very many appear rather large and very conspicuous, but the multitude of small ones is truly unfathomable." Some of Galileo's contemporaries reacted enthusiastically. His discoveries ignited the imagination of scientists and non-scientists alike all over Europe. The Scottish poet Thomas Sigurd wrote, "Columbus gave men lands to conquer by bloodshed. Galileo knew what's harmful to none. Which is better?" Sir Harry Wotton, an English diplomat in Venice, managed to get hold of a copy of the Sidereus Nuncius the day that the book appeared. He immediately forwarded it to King James I of England, accompanied by a letter that read in part, "I send here unto His Majesty the strangest piece of news, as I may justly call it, that he hath ever yet received from my part of the world, which is the annexed book come abroad this very day, of the mathematical professor of Padua, who by the help of an optical instrument had discovered 4 new planets rolling about the sphere of Jupiter, besides many other unknown fixed stars. Entire volumes can be written, and indeed have been written about all of Galileo's achievements, but this lie beyond the scope of the present book. Here I only want to examine the effect that some of these astounding revelations had on Galileo's views of the universe, in particular what relation, if any, did he perceive between mathematics and vast unfolding cosmos. The Great Book of Nature. The philosopher of science Alexander Koire, 1892 until 1964, remarked once that Galileo's revolution in scientific thinking can be listed to what essential element: the discovery that mathematics is the grammar of science. While the Aristotelians were happy with a qualitative description of nature, and even for that they appealed to Aristotle's authority, Galileo insisted that scientists so listen to nature itself, and that the keys to disappearing the universe balanced by mathematical relations and geometrical models. The stark differences between the two approaches are exemplified by the writings of prominent members of the two camps. Here the Aristotelian Geo let us conclude therefore what he who does not want to walk in darkness must consult Aristotle, the excellent interpreter of nature, to which another Aristotelian, the peasant philosopher Vincenzo di Grazia, adds. Before we consider Galileo's demonstrations, it seems necessary to prove how far from the truth are those who wish to prove natural facts by means of mathematical reasoning, among whom, if I am not mistaken, is Galileo. All the sciences and all the arts have their own principles and their own causes by means of which they demonstrate the special properties of their own object. It follows that we are not allowed to use the principles of one science to prove the properties of another. The emphasis is mine. Therefore, anyone who thinks he can prove natural properties with mathematical argument is simply demented, for the two sciences are very different. The natural scientist studies natural bodies that have motion as their natural and proper state, but the mathematician abstracts from all motion. The idea of hermetic compartmentalization of the branches of science was precisely the type of notion that infuriated Galileo, and the Draup's treatise on hydrostatics, discourse on floating bodies, introduced mathematics as a powerful engine that enables humans to truly unravel nature's secrets. I expect a terrible rebuke from one of my adversaries, and I can almost hear him shouting in my ears that is that it is one thing to deal with matters physically and quite another to do so mathematically, and that geometers should stick to their fantasies and not get involved in philosophical matters where the conclusions are different from those in mathematics. As if truth could ever be more than one, as if geometry nowadays was an obstacle to the acquisition of true philosophy, as if it were impossible to be a geometer as well as philosopher, so that we must infer a necessary consequence that anyone who knows geometry cannot know physics, and cannot reason about and deal with physical matters physically. Consequences no less foolish than that of a certain physician who, moved by a fifth spleen, said that the great doctor Aquapendente, the Italian anatomist Hieronymus Favicius, 1537 until 1619, of Aquapendente, being a famous anatomist and surgeon, should content himself to remain his scalpels and ointments without trying to effect cures by medicine, as if knowledge of surgery was opposed to medicine and destroyed it. A simple example of how these different attitudes toward observational findings could completely alter the interpretation of natural phenomena is provided by the discovery of sunspots. As I noted earlier, the Jesuit astronomer Christopher Scheiner observed these spots competently and carefully. However, he made the mistake of allowing his Aristotelian prejudices of a perfect heaven to color his judgment. However, consequently, he discovered that the spot did not return to the same position and order. He was quick to announce that he could free the sun from injury of spots. His premise of celestial immutability contained this imagination and prevented him from considering the possibility that the spots could change even beyond recognition. He therefore concluded that the spots had to be stars orbiting the sun. Galileo's course of attack on the question of the distance of the spots from the sun's surface was entirely different. He identified three observations that needed an explanation. First, the spots appeared to be thinner when they were near the edge of the solar disk than they were near the disk center. Second, the separations between the spots appeared to increase as the spots approaches approach the center of the disk. Finally, the spots appear to travel faster near the center than close to the edge. Galileo was able to show with a single geometrical construction that the hypothesis that the spots were contiguous to the surface of the sun and were carried around by it was consistent with all the observational facts. His detailed explanation was based on the visual phenomenon of a shortening on the sphere, the fact that shapes appear thinner and closer together near the edge. Figure 90 demonstrates the effect of cycles drawn on a spherical surface. The importance of Galileo's demonstration for the foundations of the scientific process was tremendous. He showed that observational data become meaningful descriptions of reality only when embedded in an appropriate mathematical theory. The same observations could lead to ambiguous interpretations unless understood in a broader theoretical context. Galileo never gave up an opportunity for a good fight. His most articulate exposition of his thoughts on the nature of mathematics and of its role in science appears in another polemic publication as the Assayer. The Billion Master fully written texts became so popular that Pop Urban League head pages from it read to him during his meals. Oddly enough, Galileo's central thesis in the Assayer was patently wrong. He tried to argue that comets were really phenomena caused by some quirks of optical refraction on this side of the moon. This entire story of the Assayer sounds a bit as if it were taken from the libretto of an Italian opera. In the fall of 1618, three comets appeared in succession. The third one in particular remained visible for almost 3 months. In 1819, Horatio Grassi, a mathematician from the Jesuit Collegio Romano, anonymously published a pamphlet about his observations of these comets. Following in the footsteps of the great Danish astronomer Tycho Brahe, Grassi concluded that the comets were somewhere between the moon and the sun. The pamphlet might have gone unnoticed, but Galileo decided to respond, having been told that some Jesuits took Grassi's publication as a blow to Copernicanism. His reply was in the form of lectures largely written by Galileo's His reply was in the form of lectures largely written by Galileo himself, that were delivered by Galileo's disciple Mario Guiducci. In the published version of these lectures, the discourse on the comets, Galileo directly attacked Grassi and Tycho Brahe. This time it was Grassi's turn to take offense. Under the pseudonym of Lothario Sassi, and posing as one of his own students, Grassi published an acrimonious reply criticizing Galileo in no uncertain terms. The response was entirely astronomical and philosophical balance, on which the opinions of Galileo Galilei regarding comets are weak, as well as those represented in the Florentine Academy by Mario Guiduccio in defense of his application of Tycho's methods for determining distances. Grassi, speaking as if he were his student, argued, "Let it be granted that my master followed Tycho. Is this such a crime? Whom instead should he follow? Ptolemy, the Alexandrian originator of the heliocentric system, whose followers trod a Titan by the outthrust sword of Mars, not made closer. Copernicus, but he who is pious will rather call everyone away from his and will spurn and reject his recently condemned hypothesis. Therefore, Tycho remains as the only whom he may approve of as our leader among the non-coxes of the stars." This text beautifully demonstrates the fine line the Jesuit mathematicians had to walk at the beginning of the 17th century. On one hand, Grassi's criticism of Galileo was entirely justified and penetrating insightful. On the other, by being forced not to commit to Copernicanism, Grassi, had imposed upon himself a straitjacket, that impaired his overall reasoning. Galileo's friends were so concerned that Grassi's attack would undermine Galileo's authority that they urged the master to respond. This led to the publication of the essay in 1623. The full title explained that in the document I work with a fine and accurate balance the contest of astronomical and philosophical weighing scales of Lothario Sarsi of Siguenza. As noted above, the essay contains Galileo's clearest and most powerful statement concerning the relation between mathematics and the cosmos. Here is the remarkable text. I believe Sarsi is firmly convinced that it is essential in philosophy to support oneself by the opinion of some famous author, as if, when our minds are not wedded to the reasoning of some else or of someone else, they ought to remain completely barren and sterile. Perhaps he thinks that philosophy is a book of fiction created by some men like the Iliad or Orlando Furioso, an epic 16th century poem by Ludovico Ariosto. Books in which the least important thing is whether what is written in them is true. Sarsi, this is not how matters stand. Philosophy is written in that great book whichever lies before our eyes, I mean the universe, but we can understand it if we do not first learn the language and grasp the characters in which it is written. It is written in the language of mathematics, and the characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to comprehend a single word of it, and without which one wanders in vain through a dark labyrinth and persists in it. Mind-boggling, isn't it? Centuries before the question of why mathematics was so effective as a planning tool was even asked, Galileo thought he already knew the answer. To him, mathematics was simply the language of the universe. To understand the universe, he argued, one must speak this language. God is indeed a mathematician. The full range of ideas in Galileo's writings paints an even more detailed picture of his views on mathematics. First, we must realize that, to Galileo, mathematics ultimately invents geometry. Rarely was he interested in measuring values in absolute numbers. He described phenomena mainly with proportions among quantities in relative terms. In this again, Galileo was a true disciple of Archimedes, whose principle of the Lagrange method of comparative geometry he used effectively and extensively. A second interesting point, which is revealed especially in Galileo's last book, is the distinction he makes between the role of geometry and logic. The book itself discusses and mathematical demonstrations concerning two new sciences. Is written in the form of lively discussions among three interlocutors, Salviati, Sagredo, and Simplicio, whose roles are quite clearly demarcated. Salviati is effectively Galileo's spokesman. Sagredo, the Scottish philosophy lover, is a man whose mind has already escaped from the illusions of Aristotelian common sense, and who can therefore be persuaded by the strength of the new mathematical science. Simplicio, who in Galileo's previous work was portrayed as being under the spell of Aristotelian authority, appears here as an open-minded scholar. On the second day of the argument, Sagredo has an interesting exchange with Simplicio. Sagredo, what shall we say, Simplicio? What Must we not confess that the power of geometry is the most potent instrument of all to sharpen the mind and dispose it to reason, reveal, and to speculate? Didn't Plato have good reason to want his purpose to be first grounded in mathematics? Simplicio appears to agree, and he introduces the comparison with logic. Simplicio, truly, I begin to understand that although logic is a very excellent instrument to govern our reasoning, it does not compare with the sharpness of geometry in awakening the mind to discovery. Sagredo then sharpens the distinction. Sagredo, it seems to me, the logic teaches how to know whether or not reasoning and demonstrations already discovered are conclusively, but I do not believe that it teaches how to find conclusive reasoning and demonstrations. Galileo's message here is simple. He believed that geometry was the tool by which new truths are discovered. Logic, on the other hand, was to him the means by which discoveries already made are evaluated and critiqued. In chapter 7, we shall examine a different perspective according to which the whole of mathematics stems from logic. How did Galileo arrive at the idea that mathematics was nature's language? After all, a philosophical conclusion of this magnitude could not have suddenly materialized out of thin air. Indeed, the roots of this conception can be traced all the way back to the writings of Archimedes. The Greek master was the first to use mathematics to explain natural phenomena. Then we are told to passing to some medieval calculators and Italian called mathematicians. The nature of mathematics gained the status of a subject worthy of discussion. Eventually, some of the Jesuit mathematicians of Galileo's time, Christopher Calvius in particular, also acknowledged the fact that mathematics might occupy some middle ground between metaphysics, the philosophical principles of the nature of being, and physics and physical reality. In the previous prolegomena to his comments on eclectic elements, Calvius wrote, since the mathematical disciplines deal with things which are considered apart from any sensible matter, although they are immersed in material things, it is clear that they hold a place intermediate between metaphysics and natural science if we consider the subject matter. Galileo was satisfied with mathematics as the mere go between the content. He took the troubled step of equating mathematics with God's native language, with God's native tongue. This identification, however, raised another serious problem, one that was about to have a dramatic impact on Galileo's life. Science and technology. According to Galileo, God spoke in the language of mathematics and in the shining nature. According to the Catholic Church, God was the author of the Bible. What was one to make then of those cases where the mathematically based scientific explanations seem to contradict the scriptures? The theologians of the 1546 Council of Trent answered in no uncertain terms, no one relying on his own judgment and distorting the sacred scriptures according to his own conception, shall dare to interpret them contrary to the sense of which Holy Mother Church, to whom it belongs to judge of the true sense and meaning, has held or does hold. Accordingly, when in 1616 theologians were asked to give Accordingly, when in 1616 theologians were asked to give their opinion on Copernicus' heliocentric cosmology, they concluded that it was formally heretical, since it explicitly contradicts in many places the sense of the Holy Scripture. In other words, what was truly at the heart of church conception to Galileo's Copernicanism was not so much the removal of the Earth from its central position in the cosmos, but rather the challenge to the Church's authority in interpreting the Scriptures. In a climate in which the Roman Catholic Church was already feeling embattled by controversies with Reformation theologians, Galileo and the Church were on a clear collision course. Events started to unfold rapidly toward the end of 1613. Galileo's former student Benedetto Castelli made a presentation of the new astronomical discoveries to the Grand Duke of Tuscany and his entourage. Predictability, he was pressured to explain the apparent discrepancies between the Copernican cosmology and some biblical accounts, such as the one in which God stops the sun and the moon in their courses to allow Joshua and the Israelites to complete their victory over the Amorites in the Ayalon Valley. Even though Castelli reported that he behaved like a champion in defending Copernicanism, Galileo was somewhat disturbed by the news of this confrontation, and he felt compelled to express his own views about contradictions between science and Holy Scriptures. In a long letter to Castelli dated December 21, in December 20, 21st, dated December 21, 1613, Galileo writes, "It was necessary, however, in the Holy Scripture, in order to accommodate itself to the understanding of the majority, to say many things which apparently differ from the precise meaning. Nature, on the contrary, is inexorable and unchangeable, cares not whether her hidden causes and modes of working are intelligible to the human understanding or not, and never deviates on that account from the prescribed laws. It appears to me, therefore, that no effect of nature which experience places before our eyes, or its necessary conclusion derived from evidence, should be rendered doubtfully by passages of Scripture which contain thousands of words admitting of various interpretations, for every sentence of Scripture is not bound by such rigid laws as is every effect of nature. This interpretation of the biblical meaning was clearly at odds with that of some of the most stringent theologians. For instance, the Dominican Domingo Bañez wrote in 1584, "The Holy Spirit not only inspired all that is contained in the Scripture, he also dictated and suggested every word with which it was written." Galileo was obviously not convinced. In his letter to Castelli, he added, "I am inclined to think that the authority of all Scripture is intended to convince men of those truths which are necessary for their salvation, and which being far above man's understanding, cannot be made credible by any learning or any other means the revelation by Holy Spirit, but that the same God that has endowed us by his senses, reason, and understanding, does not permit us to use them, and desires to acquaint us any other way with such knowledge as we are in a position to acquire for ourselves by means of those faculties, that it seems to me I am not bound to believe, especially concerning those sciences about which the whole Scripture contains only small fragments and varying conclusions. And this besides the case with astronomy, of which there is so little that the planets are not even all enumerated." A copy of Galileo's letter made it to the Congregation of the Holy Office in Rome, where affairs concerning faith were commonly evaluated, and especially to the influential Cardinal Robert Bellarmine, 1542 until 1621. Bellarmine's original reaction to Copernicanism was rather moderate, since he regarded the entire heliocentric model as a way to save the appearances in the manner of those who have proposed epicycles but do not really believe in their existence. Like others before him, Bellarmine too treated the mathematical models put forth by astronomers as merely convenient gimmicks designed to describe what humans observe without being anchored in a physical reality. Such saving the appearances devices here do not demonstrate that the earth is really moving. Consequently, Bellarmine saw no immediate threat from Copernicus' book De Revolutionibus, even though he was quick to add that to claim that the earth was moving would not only irritate any or scholastic philosophers and theologians, but also harm the Holy Faith by rendering Holy Scripture false. The full details of the rest of this tragic story are beyond the scope and main focus of the present book, so I describe them only briefly here. The congregation of the Index banned Copernicus' book in 1616. Galileo further attempts to rely on numerous passages from the most revered of the early theologians, Saint Augustine, to support his interpretation of the relation between the natural sciences and scripture did not gain him much sympathy, in spite of articulate letters in which his main thesis was that there is no disagreement other than superficial between the Copernican theory and the biblical text. The theologians of his day regarded Galileo's arguments as an uninvited foray into their domain. Cynically, these same theologians did not hesitate to express opinion on scientific matters. As the dark clouds were gathering on the horizon, Galileo continued to believe that the reason would prevail, a huge mistake when it comes to challenging faith. Galileo published his dialogue concerning the two world systems in February of 1632. Figure 20. Figure 20 shows the frontispiece of the first edition. This polemical text was Galileo's most detailed exposition of his Copernican ideas. Moreover, Galileo argued that, that by pursuing science using the language of mechanical equilibrium and mathematics, human could understand the divine mind. Put differently, when a person finds a solution to a problem using proportional geometry, the insights and understanding gained are godlike. The church's reaction was swift and decisive. The circulation of the dialogue was forbidden as early as August of the year of its publication. In the following month, Galileo was summoned to Rome to defend himself against the charges of heresy. Galileo was brought to trial on April 12, 1633, and he was found vehemently suspect of heresy on June 22, 1633. And he was found vehemently suspect of heresy on June 22, 1633. The judges accused Galileo of having believed and held a doctrine which is false and contrary to the sacred and divine scriptures, that the sun is the center of the world and does not move from the east to west, and that the earth moves and it is not the center of the world. The sentence was harsh. We condemn you to the former prison of this holy office during our prison, and by way of salutary penance we enjoin that for 3 years to come you repeat once a week the 7 penitential psalms, reserving to ourselves liberty to moderate, commit, or take off, in whole or in part, the aforementioned penalties and penance. The devastated 70 years old Galileo could not withstand the pressure. His pride broken, Galileo submitted his letter of abjuration, in which he committed to abandon completely the false opinion that the sun is at the center of the world and does not move, and that the earth is not the center of the world and moves. He concluded, therefore, desiring to remove from the minds of your eminences and of all the faithful Christians, this vehement suspicion justly conceived against me with sincere heart and unfeigned faith I abjure, curse and detest the aforesaid metaphors and heresies and generally every other error, heresy, and sect whatsoever contrary to the Holy Church, and I swear that in future I will never again say or assert, verbally or in writing, again anything that might furnish occasion for a similar suspicion regarding me. Galileo's last book, Discourses and Mathematical Demonstrations concerning two new sciences, was published in July 1638. The manuscript was smuggled out of Italy and was published in Leiden in Holland. The content of this book, truly and powerful, expressed the sentiment embodied in the legendary words "a pur si muove," and yet it moves, and the defiant phrase, commonly put in Galileo's mouth at the end of his trial, was probably never uttered. On October 31, 1992, the Catholic Church finally decided to rehabilitate Galileo, recognizing that Galileo was right all along, but still avoiding direct criticism of the Inquisition. Pope John Paul II said, paradoxically, Galileo, a sincere believer, proved himself more perspicacious on this issue, apparent discrepancies between science and the scriptures, that his theologian adversaries, the majority of theologians, did not perceive the formal distinction that exists between the Holy Scripture in itself and its interpretation, and this led them unduly transferring to the field of religious doctrine an issue which actually belongs to scientific research. Newspapers around the world has a feast. The Los Angeles Times declared, "It's official, the Earth revolves around the Sun, even for the Vatican." Many were not amused. Some saw this mea culpa, but the Church has far too late. The Spanish Galileo scholar Antonio Beltran Mari noted, "The fact that the Pope continues to consider himself an authority capable of saying something relevant about Galileo and his science shows that, on the Pope's side, nothing has changed. He is behaving in exactly the same manner as Galileo's judges, whose mistake he now recognizes. To be fair, the Pope himself in a knowing situation, any decision on his part, whether to ignore the issue and keep Galileo's condemnation in the books, or to finally acknowledge the church error, was like to be criticized. Still, at the time when there are attempts to introduce biblical creationism as an alternative scientific theory under the thinly veiled title of intelligent design, it is good to remember that Galileo already fought this battle almost 400 years ago and won.